important measure is Euclidean distance. Now, Euclidean distance may not be applicable in all cases. Maybe in all applications, it will not be applicable. For example, think of a news vendor who is basically giving the newspaper to different people in different locations in a municipality. So he or she cannot go to the shortest distance, that the perpendicular distance between his place and the location where he wants to use the. So to capture such distance, Manhattan distance or city block distance is considered. Now, in the right hand topmost figure, right hand side, I have given another measure. Suppose you think of two vectors A and B, and you want to know that how much alike they are, and there we can use cosine similarity, or that means the angle between the two vectors. Then another one, like in the bottom of figures, the left hand side, you just see that it is a concept of two events A and B. So the A intersection B, which is the middle one, that basically talks about what is the overlap in terms of the event occurrences. Now here also we can create that similarity by considering that A intersection B by A union B. So when you have some kind of categorical features, that time maybe when only the occurrence or no occurrence or some kind of different categorical occurrences are there. So many times we may go for this kind of distance measures, which is called Jacob. Then another one, which is basically the talk of today, is the Mahalanobis distance, because we in machine learning or in statistics, what actually happens that we have multiple features, and these features are in statistics we say variables. In machine learning, many times we say features, sometimes we say attributes, which basically governs the behavior of the system. How someone will behave depends. For example, whether I will be able to repay the loan or not, it depends on my income level, my attitude towards towards the rules and regulation, some kind of things. So under such situation, what happened? The Mahalanobis distance, which is basically in the statistical space, that is basically used. So somebody is speaking, please mute yourself.
Participants, you're all requested to mute yourself. Satyajit, you're requested to mute yourself. Satyajit, you're requested to mute yourself.
Could you please mute from your side?
Yeah, we will mute from our side, sir. Just a minute. Geeta ma'am, can you please mute all participants?
Please mute him, because something odd is in there. Okay, so let me then I think actually what I'm trying to tell you, that the subject matter of discussion today is that the cosine similarity and its limitations and its further developments, and how those developments will help in machine learning applications. So that is the main reason I have started with the similarity measures. So there are the 5 similarity or distance measure I have plotted, given, shown here. There could be other similarity or distance measures also. So our primary concern here is that cosine similarity. Now cosine similarity is very much applicable in the Euclidean space, but when it comes to the Mahalanobis space or statistical space, so there is possibility of information distortion, or I can say the performance distortion if we use traditional cosine similarity. That will similarity in either in classification, clustering, or some kind of machine learning applications. So now I want to discuss a little bit of cosine similarity, and this is known to all of us. It is nothing but if we consider xj and xi, these two vectors. Here the two vectors are represented in two-dimensional space for the visibility point of view. So, but this could be multidimensional. So when xi and xj are two vectors and is represented by the features or the variables which are used to measure these two vectors. So otherwise you can see that xi and xj are two data points, and which are measured using the characteristics or the features used to measure those objects, individuals, or that particular situation. So then, as I told you, that the cosine similarity is the cos theta. So all of us know that what is the formula for cosine similarity. It is nothing but the dot product of these two vectors divided by their norms. That means the that xi bar and xj bar, that norm, if you adjust, then this will give you the cosine similarity. Now, what is the application of this, or how do we interpret this cosine similarity? So if the angle is close to 0, so that means cos theta is 1. So they are similar vectors. If angle is close to 180 degree, so then the cos theta value will be -1. So it will be opposite vectors. If angle is close to 90, it is almost 90 degree in the sense perpendicular in nature, is orthogonal. So similarity point of view, if the perpendicular vectors are that quite dissimilar, because cos theta will be 0 at that time, I can say perfectly dissimilar. They are perpendicular to each other. Now, this similarity measure, where it is used in machine learning. See, it is used in classification. For example, when you use K Nearest Neighbourhood method, there actually we find out that that how many neighbors, that K neighbors you want to first you consider, then an individual or object, for which what you will do, you will find out that what is the distance of these objects with this K neighbor, and that way groups are formed, classification is made. Similarly, in clustering, where K-mean clustering, what we do basically, again, there we will use some distance, because suppose there are K clusters, some objects belongs to, suppose, cluster 1, and some maybe belongs to cluster K, and some other belongs to other clusters. So then what is the distance between this cluster and the objects we are interested in? And then depending on the smallest distance, so the new object or the object of interest will be put under that the lowest distance cluster. So that means you just see that distance and the similarity applications, few applications I show, classification, clustering. Now, recommendation in the sense, if you want to recommend a product to a particular customer segmentation, definitely the product feature should match with the customer group. Okay, so similarly, information retrieval, if we are looking for a particular type of information, and then when you gone through or search through different documents, then you may find out this kind of, again, that what is the similarity, and you will do this. So the purpose is group similar instances, classify unknown samples, recommend similar samples, detect outliers, so many things are there. Some of the practical applications, what I have started with, just I am highlighting little more. One is market segmentation, finance fraud detection, psychometrics and personality analysis, speaker verification from audio processing, outlier and anomaly detection, accident path modeling, which Satyajit is doing using this modified Cosine similarity, and document classification and labeling. So need not be that these are the only practical applications. You will find out several practical applications, and you have to understand, just find out what are the machine learning or deep learning or statistical methods that use distance measures, and then you can simply understand that some of the distance measures can be used, and there are certain application area where Cosine similarity is important, and certain area where maybe Mahalanobis distance, simple Mahalanobis distance important. Certain cases you have to modify the things. So what are the limitations of Cosine similarity? Now you just see the left hand figure. This is a bivariate scatter plot, and this scatters basically, or this data is generated from a bivariate Gaussian population, or other way I can say that bivariate normal distribution. Now, bivariate in the sense there are two features, x1 and x2, which basically governing the behavior of this population. Now, all the dots, green dots, these are nothing but the observations. If each of the dots can represent objects or individuals or items. For example, if we think that this is nothing but the scatter between maybe experience and income of some population, then each of the points represent the individuals, and x1 and x2 represent their income and experience kind of things. Now my question here is, I have chosen 3 points, means 3 individuals or 3 objects, A, B, and C. So if you use cosine similarity, that means the angle between the vector A and B, angle between vector B and C, and angle between vector A and C. So in that case, you may find out that basically C, if I consider angle between A and B is very small angle compared to angle between A and C, or maybe B and C, some kind of things. So what happened actually, you may find out that even when you use cosine similarity, so there may be some of the points which are looks to be dissimilar, but in statistical sense they are more similar. So here, if you see the scatter, in the scatter, the scatter, so B and C, these 2 individuals or objects or items, they belong to the general mass. But whereas A is little out of the general mass. So statistical sense, A is not as similar to B and C, means BC in statistical sense is more similar than A. So that kind of, that means the variance and covariance adjustability is not there in traditional cosine similarity. The reason is simple, because cosine similarity is accurate only in the Euclidean space. Whereas most of the time in machine learning, multivariate data generally resides in statistical space. So we have to have a cosine. If we want to use cosine similarity, then ultimately you have to adjust the data with the covariance structure. So that's why we proposed the variance adjusted cosine similarity. Now let us see that how we are doing this. So before going to our development, we have searched that what is the literature talking about the limitations of cosine similarity. We have not got much, perhaps maybe limitations of our search, but whatever may be the issue, ultimately it is obvious that there is not much literature which basically dealing with the limitations. What we have found out that under such situations, like Nguyen and Bai, they talked about that you do the linear transformation of the data. That means the data collected, and then you, after that, you use cosine similarity. Goldberger talks about that some kind of inverse square root of positive definite matrix they have considered, and they also found that the result is better after this transformation. But to the best of our knowledge, so they have not explicitly mentioned the variance and covariance structure of the feature vectors or the features. So as a result, and also that means the concept of statistical distance is not that way explicitly told by these two authors in terms of the covariance and variance covariance structure. That is what is our understanding. If we are wrong, then definitely some more, if development has taken place, we will appreciate all those things. So what is our proposal? Our proposal is that, okay, we will use the traditional cosine similarity, but we modify it, adjusting the variance of each of the features. Because you see, if you see this figure, then obviously you will find out that x1 variability and x2 variability are not same. Whereas if you go for Euclidean distance, then it is basically considered that same. Second one is here the data is having some kind of correlation. So that means the covariance is also present between x1 and x2. So these motivated us just to use statistical distance. Now again, in statistical distance, later on will show you that it requires the variance covariance matrix to be computed, and its inverse is needed to be computed. So that is a computationally challenging when it is a very big data set is coming, and there are other problems also will come. So that's why, to make the computation a little easier, and the Chloesky decomposition is used. And obviously Chloesky decomposition can be used only when the covariance matrix is positive, semi-definite, positive definite, or kind of matrices, positive definite matrix. So I'm not sure that how much I have been I mean I am able to give you so far, but the gist is like this: that cosine similarity talks about similarity between two vectors. Cos theta is the measure of similarity. Now cosine similarity works in the Euclidean space correctly. But in machine learning applications, when we do classification, clustering, or that hybridization of all those things, what will happen? We use multiple features, which are nothing but the variables. And these features are basically statistical in nature. And then what will happen? That means they will vary, may not vary. or there will be correlation, covariance, or other way covariance. So many things are there. So the space is different. It is not the Euclidean space. It is the statistical space. So if you want to use variance cosine similarity in the statistical space, so what are the developments? What could be developed? So there could be many, but so far we have identified a few which are not as direct as ours. But I am sure that there could be many other ways people are looking for. But our development is that let us take the statistical distance first. If you see this slide, I am talking about derivation of VACS. Here at the top, I have given you the formula, which is statistical distance formula. Here, X is nothing but the feature vector. Mu is that mean vector that of each of the feature has a mean vectors. And sigma, capital sigma, is the covariance matrix. We say covariance matrix or variance covariance matrix. So what is happening here? You are basically adjusting two things. You are making each of the data that vector mean subtracted, x minus mu. So that means you are bringing it to zero origin. And another one is sigma inverse. That is basically you are dividing the corresponding that variance covariance structure for this case. So that means it is mean subtracted variance adjusted distance. So that is known as statistical distance. And if you take each and every point, then for point xi or xj, some I or j will be using. And when sigma is not available, that is the sigma is nothing but the population covariance matrix is not available. For large data set, we can use sample covariance matrix, which is S. If you use sample covariance matrix, then this distance will be known as Mahalanobis distance. So as sigma inverse, getting sigma inverse for sparse data, when you are, suppose you are using the text analytics kind of things, where that means document to vector kind of that transformation you have made. So there are many keywords. So ultimately it will be a very large matrix, and you will find out in many places there are zeros. So sparse data. So under such situation, that getting the covariance inverse of the covariance matrix will be very difficult. So then we thought that Chloesky decomposition will improve. Now, what is Chloesky decomposition? Chloesky decomposition is nothing but that covariance or a square. A covariance matrix is a square and positive definite we are considering. And you make this matrix into two parts. One is lower triangular, that you convert it into a LU, lower triangular matrix only, not LU, only lower triangular matrix. So here the lambda, capital lambda, is the lower triangular decomposition of the covariance matrix. So we are not going into that how this decomposition is taking place, because these are standard matrix decomposition available in any textbook. But what is interesting is that if we decompose in this manner, so now then computing the sigma inverse will follow the equations what we have given you, and also the statistical distance will be converted to x minus mu transpose lambda transpose inverse lambda inverse x minus mu. So I'll show you some more about the derivation. So now these are all mathematical way of doing mathematical or algebraic way, you can say, matrix algebra. So now we have done that kind of manipulation, and finally what is happening that we got the equation 2, and this equation 2 nothing but, if we consider, is basically talking about Z transpose Z kind of situations. Okay, and where Z is this. So what we are trying to tell you here, That means this lambda, capital lambda inverse, when it is multiplied by with the data vector, and then what will happen? The statistical distance is basically transformed to a new vector space, and in this space the cosine similarity will work, because cosine similarity works well in the Euclidean space. So then what actually we have done here? We said that fine, you have the that multiple features defining the population, and the features are basically at statistical, they are good at statistical space, they are measured at statistical space. I want to use cosine similarity in the statistical space. So what you have to do then you convert the variance covariance structure using Chloesky decomposition, and once the lower triangular matrix you get the inverse of this when it is multiplied with the input data, that X, then you ultimately converting this to a new vector space where that cosine similarity will work. So so these are the things, but issue is that any similarity or distance measures require certain properties to be satisfied, and here some of the properties we have given, that what this lambda inverse, that means when we multiply with X, these values will satisfy. So you just see that what we are saying, that when mu is 0, that means things are mean centered, and then the matrix become lambda inverse X transpose then lambda inverse X, and this is the properties what it satisfied, it is similar to the Euclidean space. So the now new vector space is Euclidean space. This is basically we can say that some kind of proof. Now there is no problem in applying the traditional cosine similarity with this transformation. So if you want to calculate cosine similarity, what you have to do? You have to have the variance covariance matrix of the features vector, and then do the Chloesky decomposition, then get the lower triangular, that lambda, and compute the lambda inverse, multiply with this X. So, and then you use the cosine similarity traditional formula with this transform data. Now whatever development have taken place, let us see that how it can be used in classification. So we have considered only two class problem. One is that is y equal to 1 or y equal to -1. So means if you think of an example, suppose you think of a supply chain problem where the supplier selection is a key issue. Now question is, there could be two group of suppliers whose quality, one group is good at servicing, that means the service quality of that supplier is good, another group may be not good. Not good may be moderate or maybe poor also. So if we create these two kind of situations, that okay, I have to stick to the good supplier and I have to go for new supplier who will be equally good. So under this situation, so given the supplier characteristics, so you can put them either class 1 or -1. Class 1 means suppose good supplier, -1. This kind of applications. Now here, obviously, if we say that customer supply point of view, then lead time is important, the quality of the item supply is important, and then what other things are important, that whether damage or demerit, so many things are important, whether they are meeting the deadline or not, so many features you can consider. And now our approach is that if the customer supplier are good supplier, then they come from one population, and if they are not good, then they are coming from another population. So that means for the in classification problem, when y equal to 1, it has a covariance matrix sigma y equal to 1. So y equal to minus 1, it has another sigma y equal to minus 1. So that means their covariance matrix also will be different. And these are population covariance matrices. So then for these two, the corresponding lower triangular matrices will be one for the good supplier, another one for the poor supplier kind of things will be like this. Now see what happened, the same cosine similarity here, the formula we have written in the transformed data, that is lambda inverse x dot lambda inverse that x I and j. Ij represent the object, ith object or jth object. Here, if I talk about the supplier, then the ith supplier and jth supplier. And this normalization, other things are being done. This K we have given just to say that there are two class 1 and class 2. But issue is, when we talk about supplier or any or customer or anybody whose features or whose behavior we are interested to know, but what is that population? It is very difficult to have full knowledge, complete knowledge about population. In statistics, most of the time we say population parameters are unknown. Then we go for sampling. And from the sample with sufficient data, if you sample, you can just estimate the population parameters. So here the same thing happened here, because sigma y equal to 1 and sigma y minus 1, mean the covariance matrix for these two class is not known. And it is, so that means we have to have some means by which we can calculate them. So here that the proposal is pseudo Euclidean. That means we propose the data be transformed to a pseudo Euclidean space, and in the pseudo Euclidean space, as there are two class, one is the class 1 and class 2, if the proportion of class 1 is p in the group, and then proportion of class 2 will be 1 minus p. So that means the good supplier and bad supplier or poor supplier, if you consider them together, suppose that is, let it be that n, maybe n is very large, then suppose n1 is basically good supplier and 1 minus n1 will be bad supplier, then proportion is basically n1 by n and 1 minus n1 by n, like something like this. So then that x Euclidean, that pseudo Euclidean, that one, this is created like this. That means we multiplied the proportion. And interestingly, this is nothing but that you will find out that expected value of the lower inverse of the lower triangular, that decomposition, that Chloesky decomposition times x. So this is interesting, because when we talk about estimation in statistics, we talk about what is the mean value of this case. So we don't know if that is lambda inverse, but through sample, if we can calculate the expected value of this. Okay, so that means what happened? This is the way how you will basically get some idea or get some value of the unknown sigmas. Now, after that, suppose now question is that, suppose you have, we discussed, I told Satyajit also, that suppose, see, when we are using the classification problem in machine learning, basically I have training data. Some new observation will come and I have to say where it is. So that means we don't have the total data, we have only training data. So from that sense, we have to infer, that is what is the machine learning does. So you have to infer from the training and for the new one, which is basically sometimes we say test, validation, but I'm going beyond that. Test is also done just to see that whether my machine learning model is working or not. But after that, it will be in use, this completely new data point will come and you have to see this. So what we are saying that as machine learning uses a large number of data, so it's a large sample case. So that means we can use the sample covariance matrix, that is instead of the earlier one, that formula what we have shown. So here we also can do the Chloesky decomposition of sample covariance matrix. Okay, so this way, what we have done, basically, we created several situations and several ways or means of improving the cosine similarity to suit with the statistical space. So with this development, now I'll show you some case. These cases are not our data, these are available data, online mostly available. So first one is the classification of breast cancer data. So what is this? This is basically data. Let me tell you that data set is obtained from the University of Wisconsin Hospital Medicine from Dr. William H. Holberg. So Satyajit has basically downloaded the data, I think, from the online source. The data set is originated from the, what is the data set? Digitized images of fine needle aspirates of breast masses. Hello? To observe how analysis of cell nucleic characteristics aids in diagnosis of breast cancer. So what is the data set information? 569 instances. There are 30 real valued features and the classes are malignant or benign. So data set consists of 357 benign cases and 212 malignant cases. So now 30 features, that in 569 observations. So you can think of a very big matrix, 569 cross 30. Okay. Now, if we consider 80% of the data for training, then that also will be more than 400. So that means it's a big matrix, 400 cross 30. So what is our objective here? That we want to predict using the VACS and obviously some classification algorithm like KNN. Okay. So, and we will show the performance with traditional cosine similarity with VACS, what actually happens. So this is the snapshot of data. So you can find out the last one is diagnosis, where M means malignant and B will be benign. So the coding and other part not required. So I'm not discussing all those things here. What we are discussing here, that you see the results and compare them. So now if you use traditional KNN, so this result is for test data or validation data, whatever we see. This is not for training data. Training results I am not showing, because training result, whether converging or not, that has been taken care of. Now with the test data, that is 20% data. Now what actually happening, you see the classification table for traditional, and if you see that, suppose F1 score or as well as other things also, precision, recall, and then you see that when we are using the KNN data transformed using expected value of W inverse, and this is nothing but basically our VACS part. So that is traditional KNN. This is basically VACS based KNN. So see, there is improvement. Yes, the improvement is not much, because traditional KNN also gives you good result, but VACS is giving you better result. Now, if you see the, suppose instead of doing going for that pseudo statistical, that Euclidean distance, what we have shown you earlier, if we straightway use the S inverse, that means covariance inverse of the sample covariance matrix, then what is finding out, that is worse, that is not giving good result. So our comparison is traditional KNN cosine similarity based classification vis-a-vis our VACS based. So we found out that there is improvement. Obviously, from the precision recall or performance measures point of view, the improvement is not significantly better, but it is at least comparable, or I can say it is little better. The real benefit is here. Now, what happened? Then we thought that let us do some sensitivity analysis with both the things. Means we will decrease your training data set. So here you see that what is the test data set? We again 20% test means 80% your training, 30% test means 70%. So like this, we increase the test data set. And then we have seen all the accuracy, all the performance measures. You just see the original one or not behaving correctly. It is showing some kind of down and up kind of situations. That is not correct. If I train with more data, it is expected that the performance will be better than when it is trained with lower data. Unless otherwise the data set is so big that even the 50% is also so big. But our VACS is giving more reasonable result, means it is decreasing, and obviously the decrease is not as that downward like this, but still it is better. It can be accepted kind of things. So one hand the accuracy, another one is sensitivity. Sometimes we may require to go for only 50% or 60% of the data as training data. Okay, so here this case study shows that VACS gives better representation or better classification. In the case study 2, it is a text analytic case study, where in text analytics you all know that that cosine similarity is used very much. Here, actually, this is OSHA Health Safety Executive Database, and it is basically maintained in US. So they have incident reports. What is the incident report? Incident report is a brief description of the sequence of events that lead to the incident, and the final outcome is whether the case is a fatal case or non-fatal case, means whether someone died or not in the accident or incident. So 500 incident reports were selected, and the purpose is same. What is the purpose? We want to see that whether VACS performs better than traditional CS or not. CS means cosine similarity. Here also we have used the KNN only. Okay. So this is a text data that is snapshot of the text data. You just see some narratives. So when narratives are there, so then you have to do a lot of work to finally come to this matrix. In order to get this matrix, that doc to VAC matrix, so that is required. So you have to do some kind of extra work. What is this? The text data of incident reports was converted into embedding matrix using doc to VAC algorithm. This is available algorithm. The embedding matrix was split into training and validation data. That is the way we do in machine learning. Then covariance matrix calculated, and the Chloesky decomposition was computed or done, and then we calculate the variance adjusted cosine similarity, and then we use KNN for this classification work. So to see the result is here. Obviously, here again, both the cosine similarity and VACS traditional, and both as far as the precision recall and other things considered, their performance is poor. Poor in I can say moderate. Means precision is 0.75 for 0, and for 1 it is 0.94. But if you see or compare the two, you will find out that our VACS approach is giving better result. So that means these two case studies shows us that the concepts that what is being developed here in our lab, it is working. That is what I want to tell. And in fact, when the things are data is in the statistical phase, I think that instead of using cosine similarity in a traditional manner, perhaps the transformation and use of this variance adjusted cosine similarity gives better result. But it needs to be proven by many more examples, and also there is some kind of theoretical underpinning from the proof point of view. So sensitivity analysis clearly says that VACS outperforms our CS, that is cosine similarity, traditional cosine similarity. Now, I want to show you that later I want to tell that I am not showing, because I have shown you two cases. So what are the things we have discussed so far? Cosine similarity is important. Cosine similarity works perfectly in Euclidean space. In other space, particularly in statistical space, cosine similarity needs to be adjusted or modified. One of the approach is variance adjusted cosine similarity, the derivations and other things we have shown. With two case study data, we have shown you that VACS is performing better than traditional cosine similarity. Now, issue is here that I have not given any example from logistics and supply chain, which is one of the important area of that FedEx. So that's why I have given some of the examples where these can be used. One is in supply chain, customer segmentation, although it is a marketing part, but it is important. Route optimization and matching is important. Inventory demand pattern matching is important. Vendor similarity, I told about the vendor quality. And warehouse layout optimization, forecasting, a few of the application area I have shown here, but there could be many more. I mean, where you are using distance measures or similarity measures from the classification point of view, clustering points of view, or any other kind of learning point of view, definitely that this approach will work, and this approach will give you good results, provided you have to understand that what distance measure is appropriate for these situations. Then what are the future works? Or I can say the conclusion is that VACS gives better results when data is transformed using the respective population covariance matrix into Euclidean space. It gives the best result. Let me repeat, we are talking about respective population covariance matrix, which is traditionally not known. If you know the population covariance matrix, then it is better to use that. So when population covariance matrix is not known, then the heuristic approach, what we have shown, that pseudo-Euclidean space, if you use, it is shown through two case studies that this gives better result than the traditional cosine distance. At least one thing I can say, that the change in the training data set, that kind of sensitivity point of view, if you look into it, VACS is much better than CS. But if you say the comparison accuracy or performance point of view, CS is a little inferior. But with these two cases and this may be small data, we cannot compare objectively, but it is promising. Then what is the future scope of work? So one of the important work is that Chloesky decomposition requires that the covariance matrix should be, or the matrix you are decomposing should be positive definite. Suppose my data set is such that it is not positive definite. So what will happen? What kind of mathematical manipulation, or I can say improvement is needed here? Now, second one is how to better estimate the population covariance matrix from training data. So, see, if you see that the development in quality domain, particularly Taguchi methods in quality engineering, so Taguchi has given a lot of that practical approach, where basically particularly from the design of experiments point of view, he has given a lot of practical approach. So if the theoretically it's not possible, but at least with a lot of data, a lot of different cases, application in different sectors, and then analyzing the results, we may come into some all practical purpose solution under this kind of situation when you have not positive definite covariance matrix. So what is the other limitation? So what I have not noted here, basically see what we have done. We have just shown you that CS, if you convert into VACS, it works better. But we have used only one machine learning algorithm. What is this? KNN. But there are many other machine learning algorithms. So if we compare other machine learning, use other machine learning algorithm also, then what will happen? So that kind of study we have not done, but obviously our scholars, they will do. And I am presenting with the hope that as this is some kind of new development from our side, so through this presentation, I want to request everybody that why can't you use, if you are working in this kind of domain, you use and see that whether our development, what we are proposing, it is really giving good results, or it has a lot of fallacies, or there are a lot many other limitations. Okay, so another work could be that this now suppose you are developing many algorithm for different devices. There might be the classification or clustering kind of that inbuilt programs are there. You might have used some of the distance measures, but if you use this distance measure, and you may see the device performance is better. So that sense, so there are many other ways it can be looked into, and we will be happy to have mails and also queries in this regard, even in future. So we are eagerly waiting for someone who will later, may not today, later will tell that these are the ways things can be improved, particularly the mathematical part and the statistical test kind of things need to be developed. With this, I want to close these, that these are the references. So the three references I have shown. I have used some of the open source, maybe net material for some of the figures. I think mostly I have cited them. If I have not cited anywhere any figure references, that is completely unintentional. And I want to end my lecture with this, that with the quote of Swami Vivekananda: in a day when you don't come across any problems, you can be sure that you are traveling in a wrong path. With this, I close. Thank you so much for giving me this opportunity.
Thank you, Professor. We will now open the session for questions. You can directly unmute yourselves and ask questions to the professor. Or you can also put your queries on the chat and we will read it out to Professor.
Hello. Thank you, sir. So it was a nice presentation and very good development. So I have a small query on it. Like, sir, I have basically two queries. The first query is that the development that you have shown, that is mostly dependent on the well, when the data follows multivariate Gaussian mostly. or linear kind of thing. So if the, let's say, data is multivariate non-Gaussian or skewed kind of thing, so whether the same development can be used or not. So this is the first query. And the second query is that how to understand that when the data, let's say you have used the OSA data, so how to understand that OSA data falls under statistical space or Euclidean space? Yes, sir.
Okay. Okay, very good question. Thank you. So, yeah, that is the first one is basically if data is multivariate Gaussian, the statistical space and all those things what we said, that is the development is purely based on this. But even if it is non-Gaussian in nature, because we are interested in the covariance matrix of the feature space. So, and you just see what we are doing here basically, that features covariance matrix. So that is basically through Chloesky decomposition, the transformation is taking place. So I cannot tell you 100% with 100% guarantee that this will work under non-Gaussian case, but as we have not tested, but I think it will work. The reason I'm telling you, particularly the case 2, when we talked about OSA data, so whether the features are Gaussian or non-Gaussian, we have not tested. We simply consider the dog to that what to dog vector, and that may not be Gaussian also. So although I started with Gaussian, bivariate Gaussian to demonstrate, but to me it will be applicable in non-Gaussian case also, where covariance matrix is available, either sample or population covariance matrix. Your second one is basically your second one is yeah. Sobik, can you repeat the second one? Statistical.
Yes, sir. Actually, that data, let's say that OSA data, whether the OSA data falls under statistical space or Euclidean space, how to understand?
Oh, that
because
is
as the you are converting the data from statistical space to Euclidean space.
In Euclidean space, if you want to understand Euclidean space, then there will be no covariance. Because data and statistical space coming because of the covariance.
Okay, sir.
So that means sigma will become I or diagonal matrix kind of things. So,
yes, sir. Yes, sir.
Okay.
Yeah, thank you, sir.
Thank you, Souvik. Professor, there's a question on the chat from Rohit. His first question is it right to say that this is distance matrix is valid only if the features have reasonable correlation?
Okay. So again, a good question. And but this will be valid if there is difference in variance also, even if the correlation is not that significant, but there should be difference in variation. And if there is correlations insignificant and variance is almost similar, then obviously that represents some kind of Euclidean space, similar to Euclidean space. So that way, you can maybe your cosine traditional cosine similarity will give you better result.
Okay. His second question is many a times in deep networks, the features extracted are quite abstract. Is this distance metric valid in such scenarios as well, beyond traditional machine learning algorithms like KNN, K-means, etc.?
What I understand from the question that that features are abstract in nature, if I am clear. So if features are abstract in nature, that means the numerical quantification is very difficult. Okay. So as distance measure use arithmetic operations, like sometimes that arithmetic operations means your addition, subtraction, multiplication, inverse kind of things. So when your features are abstract in nature, so you have to have some way of converting the abstract features to some numerical sense, where arithmetic operations possible, and as a result, you will be able to compute the covariance matrix. Otherwise, I think it is better to go for not use this. Then you, for example, the Jacob distance, what I have shown you in the first slide or second slide. So there what happened, this is basically some kind of abstract or categorical variable case. Some present, some not present, then the proportion, the probability concept is used to measure the similarity. So it is basically, it depends on the nature of the data and the measurement scale used to measure the data. Yes, Rohit, it's a very good question. So if you have such kind of data where the basically the abstract in nature, so you just see that what are the different ways abstract data can be converted some meaningful numerical data so that you can compute the covariance matrix. There are methods. Or other way I can tell you that one method is basically chi-square distance is there. Okay, so you can use chi-square distance, but again, if you use somewhere chi-square distance, somewhere Euclidean, and somewhere the statistical distance in the same data feature domain, so what will happen that aggregating them, that kind of covariance structure fusion will be difficult. So it's a very complicated one. So as a result, my suggestion is you do some simple normalization kind of thing, like maybe frequency matching. When instead of the abstract values, you take the proportions. Wherever that particular category or abstract is coming, you use the proportion value. For example, suppose three categories. 30%, 40%, and 30% is there. Whenever in the feature column, that category is coming, you put 0.3, where other category is coming 0.4, other category is coming 0.3, like this. So that is some kind of simple transformation. Achha, this is the first question. Any other question?
Yeah, both his questions are answered. He has said it's clear, and thank you, sir. We have another participant. Omkar, you can unmute and ask your question directly.
Yes, ma'am. Thank you, ma'am. Thank you so much, sir, for the session. It was really great session. So my question was based mostly on forecasting because that's of interest. So I wanted to ask, in forecasting, detect a seasonal pattern is quite easy. We have some leverage from this to detect the external variables across different product category or regions.
So your voice cut basically. Sometime can you please repeat, or you can put in the chat box?
Yes, sir. Sir, I was asking, while seasonality is a thing that we
Okay.
can get or detect easily when it comes to forecasting, external variables are hard to get. Can we use this cosine similarity in order to form a relationship between seasonality and external variables across different products or regions?
Okay. Seasonality, basically that is some kind of dummy variable you can consider here. Means what I want to, whatever by seasonality we mean, what do we mean? We mean that, for example, you think of a selling of garments, then or one product is garments, let it be. So that means the festival time the sale will be more. So that is what you are trying to tell. That means the festival time, sometimes what happened during the winter, rainy season or summer time, like AC product that sells, that summer time it will be more. So in that case, cosine similarity, better you use seasonality as a dummy variable or categorical variable kind of things. Suppose that, and then one of the features that is better.
Okay, yeah, sir, that makes sense. Thank you so much, sir.
Are there any more questions? There is a question from Anish. Since VACS uses a Mahalanobis-like transformation to enable cosine similarity in the Euclidean space, does this imply that other similarity function relying on angular measures can be made valid in a transform space if we choose an appropriate whitening strategy?
I think so. I think it is, because whatever may be there, because ultimately cosine similarity works perfectly in Euclidean space. From other space, if you can find out some way of transforming the data to
वो नंदिनी स्वीट्स के पास है क्या कुछ?
then it is true. Yeah, you can do that.
Okay, Anish, have you got your answer? Okay, he says yes. Thank you, sir. Are there any other questions? Okay, so with this, we'll close the session. Thank you, Professor, for accepting our invitation and coming to the FedEx seminar series today to present your talk. It was certainly a very interesting session. And even as you were presenting, I was seeing that how this method can be used to a lot of the problem statements that we are solving at the center. So thank you very much for your time and having accepted our invitation and being present with us today.
Thank you. Thank you so much. It is my pleasure.
Okay. So just one question from Akhil. Would this technique be a promising for a shuffled and mass time series data, as we'll be losing the relation between timestamp of data point?
Can you repeat?
Would this technique be a promising one for a shuffled and masked time series data, as we'll be losing the relation between the timestamp of the data point?
Okay, so again another forecasting problem. Time series data. So the question is basically whether this can be used in time series data.
Yes, for a shuffled and masked time series data, because we'll be losing the relation between a timestamp of data point.
Okay, so that means it is basically time series data is a sequence data. Okay, sequence data. Time series means you start with time t equal to 0, maybe you end with t equal to 100. That means in the sequence. So yes, this can be used. Why? You see that in the sentiment analysis and other kind of studies, when we in the large language model, particularly the sequence, when you read a text, that means every sentence is a sequence of words, and there this word to this vector cosine similarity we use. I think it will be used, and I have not checked it, but my answer is yes.
Okay.
Hello,
right.
sir. Am I audible?
Yes, Akhil, you are.
Sir, yes, sir. Thank you, sir, for clarifying on that.
Akhil, you are not clear. Your voice is very low.
Okay. Am I audible?
Little louder. Maybe my computer is problematic. Anyhow, please.
Okay, just a second.
Go ahead. Go ahead.
I hope I'm audible now.
Yes.
So the problem I faced is I have a time series data, but the timestamps are shuffled, and we don't know the timestamp data.
Okay.
That is what the masked time series data. So how would this be applicable for such kind of data situation?
No, but how are you saying it is shuffled? Man, there no timestamp is there.
Problem statement. And the data set itself clearly mentions that it is a time series data, but with a shuffled and masked points.
Okay. No, then that you have to think differently, not use of cosine similarity at this distance. Actually, I think time series data always have certain patterns.
Okay.
So it was coupled. Maybe if you take each of the column and then plot it, you may find out that whether it is coming random or there are some kind of pattern is there, you just see. And then you do one thing, another one, that the features name you choose, because the features name are available, column names.
Yes, they are available.
So they are available. Then how? Then you see that from the name you understand that what way the pattern, logical pattern is what. What is the context? Which application area it is?
It is in the options trading domain. Basically, financial trading domain, machine learning problem.
So maybe I'll request that if this can be taken offline, Akhil, you could directly contact Professor Maiti and he would be able to help you with your question.
Just one minute. Okay. Yeah, I think see, this is a little complicated problem.
Okay.
And but what I want to tell you, if you want the timestamp back, that you want to know what is the sequence, the data, then maybe some kind of pattern analysis and then followed by the theoretical pattern of it. Means what should be the true behavior of that particular feature. Then you have multiple columns, means multiple features. So now if you see the cross relation, and if from there you may get some idea, but it is really difficult for me also.
Okay, sir.
Okay.
Thank you.
Yeah, all right. So thank you, sir, and thank you to all our participants for having joined online today. We had 60 participants attend the seminar, and I hope that it has been beneficial for you. So with this, we're closing the meeting. Thank you all once again.
Yeah, thank you so much. I'm leaving.
Sure. Thank you, sir.